Thank you very much. Merci beaucoup. It's my great pleasure to be here and to speak to mathematicians who know more about combinatorics. In fact, while we are physicists, we use combinatorics, and here I will try to advocate a new emerging field of, let's say, quantum combinatorics, or maybe better said, quantum combinatorial designs. Before discussing the subject, let me mention my collaborators, two from India, Suhail and Arul from Chennai or Madras, and three my former students. Now A.Burchardt is in Amsterdam, Wojciech Bruzda now is in Warsaw, and Grzegorz in Barcelona. Look, I prepared here a special decomposition of this year. I will explain it later. You can check that this decomposition is correct. Before going to combinatorics, let me first remind you what, in the simple words, what is quantum. Well, if you have a coin or a pen, classical pen can be oriented up or down, you have 0 or 1. And we assume in quantum case that all possible orientations of the spin or vector are possible. So therefore, okay, our state is just vector of the two-dimensional, for simplicity, Hilbert space, and then any state like this can be interpreted as a point of a sphere. You know how a sphere looks like? It is just nothing else as a complex projective space. You have here a complex number, the vector is normalized to unity. And of course, if you look at the sphere, how it looks like. All the points are the same. The sphere is isotropic. And the same is for pure states of larger dimension. It's not a sphere anymore, but something similar. It's a formally complex projective space, Cpn-1, of 2n-2 real dimensions. But again, this is in a sense similar to a sphere, as is isotropic. All the states are equal. So there are no states with extremal properties yet. And now I will say that the situation changes if you assume there are some constraints or some structure is given. Quoting the famous author, okay, it's a bit quotation change. You know, all quantum states are equal, but some states are more equal than others. You will know the original quotation. So when it is the case, for instance, if you have a composite system of two qubits, if I have two qubits like two spins, I can distinguish, this is blue one and this is red. So I have two physical particles, and now I can say, there are some states which are in our language separable. So mathematically they are just product states. And then from the geometric perspective, it is a Cartesian product of two spheres embedded in CP3, Segre embedding, or there are other states, like Bell states. So superposition of two states up and two states down. They are not of the product form. You see it here. This is just the famous Bell state. So this is our notation, 0, 0, plus 1, 1, and this is just normalization factor. So you see, we can distinguish. Some states are separable, some are entangled. And those Bell states, there's a good reason to say, they are maximally entangled in the following sense, that this partial trace of the projector is maximally mixed. I'll explain it in some words. So in some sense, you can say, first there is this CP1 times CP1 distinguished in CP3, but there will be another set of those points in CP3 which are as far as possible from this Cartesian product. And we claim that for physical purposes such states could be useful, like entanglement is useful for quantum information, and so on. So if you have any questions concerning this introduction, maybe you can pose them right now. If this is not the case, let me, this you know much better than me.
The bell is not the same what was in previous talk.
Very much. This is not the same bell, but the spelling is the same, yes? The spelling is the same, but the person is different, yes. And now I return to combinatorics. This you know better than me, so I'm very shy to tell experts about combinatorics, but let me first start with simple recreational mathematics. Recreational mathematics in the sense that we take, for instance, discrete objects, like 3 cards, and we have 3 copies of it, and we want to arrange such a square. It's called Latin square if all symbols in rows and columns are different. It's as simple as that. Of course, such objects exist for d equal 2, 3, up to, for arbitrary n. Then Euler himself, he studied more complicated case, and he wanted to have two such squares and called them orthogonal squares. Look, one is written with Greek letters, one with Latin, therefore another name is Greco-Latin square. And Greek letters form such a Latin square, Latin letters also, and orthogonal means that all those symbol sequences are different. This is a combinatorial design. In some more general sense, you can say, a design is a constellation of elements from a finite set, arranged in a special way, for instance, with some symmetry and balance. Here, this balance means there are in each row, each column, all those symbols are different. And of course, it's nice recreational mathematics, but also related to the heart of combinatorics, but also to statistics, planning of experiments, and applied mathematics. Well, so let me now go to n equal 4 and pose the very, very simple example. Let's take 16 cards, 4 aces, 4 kings, 4 queens, 4 jacks, or 4 colors, and arrange them in an array such that in every row and every column there is a single card of each suit and each rank. So how do you think? Is it possible to find a solution? Of course it is. If you have cards, well, it takes some time to see that such a solution exists. So, mathematically speaking, in the language of Euler, it is a Greco-Latin square of size 4. Very nice, yes? Very simple pattern you can check. In each column, each row, there are all suits are different, all ranks are different. By the way, for me, it is good to say, if all the colors are different, if you take average, what will be the average color in each row? Will be white. White in a general sense, because all are different. And everything is white in columns and in rows, in some sense. Well, so you see, there exists for size 3, for size 4, they do exist for size 5, so you can expect, well, if the induction principle work, they have to exist for size 6. And Euler himself was studying the problem. So here it's written that they do exist, those patterns for size 3, 4, 5, do not exist for size 2, I will explain in a second. And Euler problem looks like this. In fact, it was like, I'm joking, a grant from the military agency. You know, he was working then in St. Petersburg, and the idea is that there were 25 soldiers from 5 different regiments of 5 different ranks, and in front of the Tsar, of Imperator, they want to order in a nice way. And they did it, which was fine. But then the 6th regiment came, and there were 36 officers, and even most clever general could not order them in such a way. So he was maybe ashamed of the Emperor, asked Euler for the solution. And Euler himself worked for a few years, and he could not find the solution. Neither he could not even find the proof that solution does not exist. But he wrote in 1779 that such a solution likely does not exist. Strangely enough, the proof was given not in France, but a French, not mathematician, a lawyer, maybe you know the name, Gaston Tari, exactly was published in Compte Rendu in 1900. Do you know this story? Maybe you should. Well, he was a French person, but he was, as far as I know, he was sent to Algeria, and some people say that he had nothing better to do. And, but his great feat was, there were some like 8 million possibilities, and clever idea was to reduce them to, let's say, 3,000, and then checking one by one. But mathematically, it was also a great, great success. Moreover, he was not a professional mathematician, and some people claim that after Fermat, this was the last important result in mathematics not obtained by a professional mathematician, which is a strange statement, but maybe it's true. So it happened 121 years later after the conjecture of Euler was formulated. So look, let's make a simple attempt now in the chess notation. Let's take 6 rocks on the chessboard of size 6 and arrange them in such a way that they do not attack each other. This is very simple. You know how rock look like. Now, to make it a little bit more complicated, let's now add other pieces. Look, I have not changed the position of rocks. And now let's say I take knights and I assume that knights now do not work as knights. The assumption is the same. If there were no other figures at the blackboard, if knights were rocks, they would not attack each other. Because in each column, each row, you have different symbols. So this is nothing else as Latin square of order 6, but a single one. Because we have only ranks, so okay, ranks of the figures, or ranks of officers. But now, let's try to add uniforms, or color them. This looks like, to be simple, look, this is exactly the same pattern. I only tried to color them. I took 6 colors, and I do very well. I take first color, second, and so on. I can continue. As you can see, I was able to do 32 colors. So I'm very close, So now only 4 figures have to be, so I know which figures are missing. I have to put those 4 figures. This is simple, but then I have to color them. And here comes the problem. So this is one of the cases, let's say, checked by Gaston Tari many years ago. Because in this way you can show that for this particular constellation the solution is not possible. This is relatively easy. But now to show that for all possible initial positions, this is complicated. But you now see, the problem. And if you ask a mathematician why such a solution does not exist, it's not so simple to give the correct answer. The simplest guess is, because 6 is 3 times 2, this you know. But it makes a problem, because the construction which works for prime numbers doesn't work, and for powers of prime. And then of course you know that 6 is first number, which is neither prime nor power of prime. 2 for 2 is, it also does not exist. Okay, for 2 it does not exist because if I have here ace, I have to put here another ace. If here is k of hearts, this will not work because, okay, here, okay, let's say here are hearts, here is, okay, trump. So, okay, I already see that this king cannot go neither here nor here. So for of size 2, it does, such a pattern does not exist. Of size 6, neither. Are there any questions at this point? Is everything clear? Up till now. Good. So now we change the gears, we return to quantum, and I quote a very recent paper. Look, only 2016, Vickar and Musto had a very simple idea. It's strange that nobody thought about this before. They took standard Latin square and tried to, in a sense, quantize it. What means quantization? Well, it's not a precise formulation. It is just it is a recipe to generalize the object in such a way that it has nice properties and reduces to the, in the classical case, to known objects. So they said, let's consider the array of states, so vectors from the Hilbert space, let's say of size d, let's take d square of them, and classically, you know, in each column, each row, those symbols were different. What means different in quantum jargon? They have to be orthogonal. So the definition is extremely simple. Quantum Latin square of size 4 is the array 4 times 4 in this case, where in each row, in each columns, we have orthogonal bases. So instead of different symbols, you have orthogonal states. As simple as that. And of course, they found a nice generalization because in the standard case, you had only 4 symbols. Here you have 4 like classical symbols, and on psi and chi are just quantum superposition. They need not to be like this. This is the original example. And of course, you can see here you have combination of 2 and 3. And 2 and 3 are missing in 1 and 4, so they are orthogonal. And also here are orthogonal, so everything works. And they studied when such designs exist and how to characterize them. You understand the definition. Set of states such that there are orthogonal bases. So look, from the quantum jargon, it's interesting. Because a basis is just, for us, orthogonal measurement of Lüders von Neumann. So we have here 4 measurements row-wise, 4 column-wise. So altogether 8 different measurements, which could be different in principle. So look, standard combinatorics deals with discrete set of symbols like 1, 2, 3, 4, 5 up till d, and the permutation group. You permute the objects, yes? And the group of permutation is discrete. We have matrices of permutations. And now, in the generalized version, instead of discrete set of symbols, we have now set of states, which are of course continuous. You can rotate a state in an arbitrary way. And instead of permutation group, we have continuous unitary group. You matrices of size D. So in a sense, we embed the permutation, discrete group of permutations inside much larger object, the continuous group of unitary matrices. And I think I should mention here Gerhard Zauner and his thesis. Again, the story says, some of my educated colleagues claim this is the last piece of science which is new and important, written in German. And okay, later it was translated to English, but in a sense, at the beginning, clever people had to study this thesis auf Deutsch. And it's really amazing that it's very nice thesis, and a lot of good ideas are there. So you see, it's only 24, almost less than 25 years ago. And I think maybe the idea of quantum combinatorics goes back to this thesis. Well, so now look. We know what is Latin square, classical, quantum Latin square, and now we need to have orthogonal Latin squares and quantum orthogonal Latin squares. Okay, so what is quantization? You know, there's a nice rule of thumb that any good concept can be quantized. If the classical concept is good, you can quantize it. So here our idea is, orthogonal Latin square is a good concept, so we can quantize it. What means quantize? We look at the classical definition and look for the corresponding, more general quantum one. So, this is simple. In the classical case, all these square pairs of symbols are different. All those cards were different. So now we take, for quantum orthogonal Latin square, d square bipartite states. Now I have psi ij, which belong to this composite Hilbert space, or HA, HB, of the same dimension. And now, if they are different, I assume that all those, so A prime is the quantum analog of the classical condition. That all those d square states are mutually orthogonal. As simple as that. Case B and C are that there are no repetition of any symbol in each row, each column. So of course we have no two aces or no two spades in each row, each column. So how to quantize this condition? It's a bit more tricky. But as I mentioned, if you have no repetition, the average color is, let's say, white. And average rank is white. White means it's white because all of those symbols occur once. In quantum case, 1 means identity. You have projectors, and you assume that since this has to be true for colors and for ranks, you take partial trace of those bipartite projectors. They have to be proportional to identity for some in rows and in columns. And this is the same concerning partial trace over system A and B, which means I treat in the same way suits and ranks. This is it. Because if you take this classical object and in a sense naively quantize it, I put ace of spades into a bracket. So I consider this like king of clubs is a product state of king tensor club. This is simple. So if you consider only classical objects, then immediately you see that those definitions go back to the classical definition. So in this sense, this idea is consistent. Moreover, you see that if you take only product states, you will not have nothing more. You will have just those classical designs which are known. But of course, as I convinced you before, a part of those product states, there exist also entangled states. Yes? Yes, okay. There exist also entangled states, and those entangled states, they will contribute, they will change the problem. Well, so now we go back to composed system and entangled quantum states. I recall again, we discussed composite Hilbert space. We already know the definition. This is the product state, but not all states are of this form. This is the entangled state. This is just the state like in the Bell notation, but in our bridge notation, it's the superposition of, let's say, ace of spades and king of clubs. By the way, if you could play bridge with such superposition, it would be a certain advantage. Some of our colleagues even were thinking about quantum bridge or quantum chess. It's kind of an advantage using such cards, yes? And as I mentioned, they are called maximally entangled. In what sense? That if you take such a state, it can be decomposed in the product basis in such a way, Cij is just the matrix of coefficients. Because of normalization, its norm is equal to 1. The state is called maximally entangled if its partial trace is maximally mixed. So the entropy is maximal, which basically means that this matrix CC dagger, C is this matrix of coefficients, is proportional to identity. So the rescaled matrix is unitary. So in short, if this expansion matrix is unitary, then this state is maximally entangled. In this case, this matrix is just identity, so of course it's unitary. So we have here a nice observation that in such an expansion, if this matrix is unitary or close to unitary, the state has to be entangled. Well, this was simple for bipartite system, but now I will discuss multipartite systems. So in general, I can discuss n, let's call n an even number, n subsystems of qubits. Qubits are systems with d levels each. And we say they are called absolutely maximally entangled, AME, n qubits, if for any choice of n over 2 subsystems trace out, the state is maximally mixed. So if I have n equal to 4, if I have 4 objects, state is entangled if you have strong correlation between one subsystem and another. And absolutely maximally entangled means that for this partition you have maximal entanglement, but if you swap the splittings, let's say for this partition, you also have maximally entanglement, and for the last one, which will be this, is also maximal entanglement. So in general, for all possible choices, the entanglement is maximal. You will see soon a relation to orthogonal Latin squares. So here it's written again that such a state is here described for 4 parties by such a tensor Tijlm, if it's maximally entangled, if it's entangled with respect to all 3 possible splittings of 4 subsystems A, B, C, and D. So it means that reduced states, if you reduce over CD, or reduce over BD, or over BC, all those reductions have to be proportional to identity. So it means that the matrix U, now I use composite indices of order d square, obtained by reshaping of this tensor, is unitary, but not only unitary, it's what we call multi-unitary, because it's unitary for any reorderings. For the first reordering, that mu is ij, or the second, or the third. We have 3 different reorderings. And it happened that in the same time, this tensor were also used by other group, and they were called perfect tensor. So this is just the same. Perfect tensor has here 4 indices, and definition is simple. It is perfect if any of its flattening, so matrix of size d square, is unitary. And our is that matrix U is 2 unitary. It after of reordering indices is still unitary, which is not often the case. Okay, so now a key observation. I want to combine 2 different fields of the talk. Look, before I discuss orthogonal Latin square and its quantum analog, then I discuss those absolutely maximally entangled states. In fact, for me it's enough to have 4 parties. They are entangled for all partitions. And now I say, this is the key observation, that existence of such a quantum orthogonal Latin square of size d is equivalent to existence of such a absolutely maximally entangled state of 4 systems with d levels each. Now why 4? Look, if you have a Latin square, classical or quantum, you can encode it by 4 data. 2 digits from 1 to d determine the address in the square, and 2 others its content. So, okay, well, let me move here. So, if I have such an object here, this is the standard Greek Latin notation, this is bridge notation, this is, let's say, information notation. I have, in fact, 4 numbers, because 2 first digits are used for row and column, 3rd one for figure, and 4 for suit. So such a pattern can be encoded giving 4 numbers. And now look, from this pattern, I just explicitly construct the corresponding absolutely maximally entangled square in the following way. I take address 0, 0, and I read, Lett 0, 0. So I put first term. Then I go to the cell 0, 1, which is here. I see 1, 2. So I put here 0, 1, 1, 2. Then the next cell has address 0, 2. I read 2, 1, or let's say queen of diamond, and I put this state. And this is the second line and third line. Altogether, we have here 3 times 3, so 9 squares. And I have a state which has 9 terms. And what is now crucial? Because this is orthogonal Latin square, then partial traces over any pair of states of subsystems are white, in the sense they are maximally mixed. So this is maybe not a proof, but just hand-waving argument which shows you relation between those absolutely maximally entangled states, in this case for qubits, and the combinatorial object. This is still classical. So this is one of the key crucial points of the talk. So maybe I will pause for a while and ask you for questions.
So in your case in which you have this xi plus, xi minus, and so on, instead of one sum, and we have to put, for example, 2, 1, 0, 0 plus 2, 1, 1, 1 divided by square root 2.
Yeah, sorry. This is not normalized. Okay. So of course this should be normalized in this case 1 over square root of 9, so 1 over 3. Okay. But my point is that taking such an object, classical first, translating it into numbers, this pattern gives me the state. This is simple, but what is not so simple is that if this is a really Greek or Latin square of Euler, then this construction yields what it should, so already absolutely maximally entangled state. This is the key fact, which I hope is not so old. In fact, I hope it's new. This observation. Okay? Okay. Thank you. Yeah. So, but this is easy to check. How much money do I have? Money. How much money do I have? How much time do I have? Still some money, yeah?
Yes.
Okay, positive number.
12 minutes.
12. Okay, good number.
Is it possible
to make it shorter? Yes. Okay. Look, let's see what happens. So, you could ask to have some order for what dimensions, local dimension d and number n, those absolutely maximally states exist. It was not known up till 5 years ago or 10 years ago, nobody knew, but then our colleagues Felix Huber and Nikolai Vedelka in 2020, they had such a nice table which you can check online, it's available, and they see green is they exist, red is does not exist because of something, and white is we do not know. So now look, this is the smallest white field, which means D is 6 and N is 4. So it just corresponds to the 4 subsystems of size 6. So it's exactly a question whether in other language those quantum orthogonal Latin squares of size 6 exist. So whether the quantum version of the problem of Euler has solution. It was not known up to 21, yes?
Your n was even number before, and now you can...
Okay, well, yes, for me it was even, but they are German guys, very ambitious, so they also considered odd case. I don't need it in the stock. But it's, okay, they just, it's possible to, but you are right. Okay, for me I take only 4. Okay. I'm a modest person. No, but it can be generalized in a way. But good question, good question. Okay, so therefore we were very much excited to study this problem, and we studied it for the last 6 years. And after 4 years of study, we found a very nice approximation to this state, which was very close, but not quite. Moreover, we were able to show that if you consider, we optimize some utility function, and we could show that this utility function, it gives you the local extremum. So after another year, we're almost convinced such exact solution does not exist.
This was mostly numerical result.
Yes, it was, but numerical, but analytical was to show with this Hessian idea. No, we found it analytically, and we had very nice concrete state, which is a good approximation. Analytical one. But it's not exact. And the point is, so we started to write a good paper that such state does not exist. But fortunately, one student of Arul in India was not aware that we were writing such a paper, and he found first numerically that we were wrong, that besides our local extremum, there are other extrema which are better, and he found that such a state, in some sense, is likely to exist. So okay, I have to skip the technical details. I'll just mention one thing. We were trying to optimize some utility function over the space of dimension 1295. Why? This is 36 minus 1. So of course all random walks, they are not they are useless. The space is too huge. You need to have a kind of clever argument. And now look, do you know what is synchron algorithm? To generate bistochastic matrices. Look, let's assume this piece of paper, they are row-wise stochastic matrices. Here are column-wise. And you normalize in columns, in rows, in columns, in rows, and do it many times. And you get to this point, this algorithm converges. And you get a bistochastic matrix, which is stochastic in rows and in columns. This is a very nice theorem, nice method of synchron, like 30 years old. We did something similar, but not quite. First, here there were only 2 conditions. We had 3 conditions because there are 3 different splittings. And here this is a linear problem. You can mathematically prove it converges. In our case, there are unitary matrices, and it does not converge. So sometimes converge, sometimes not. And there are the problems. What are the problems? How to find a good seed, starting point. But if you have such a huge space, it is very difficult. So what you have to do, you have to be educated and have a good educated guess. But it's not enough, because then if you are very lucky, you find some numerical solution where you have 1,200 and so on complex numbers. What you can do with them? Not easy. Well, so to make the long story short, this is a picture of Krakow, and well, I encourage you to visit it. There are even some, you know, I'm physicist, so optical effects in Krakow, as you see. Okay, okay, and so this is the solution. I emphasize there is no classical orthogonal Latin square size 6. But there is a quantum solution. Now, what is written in this picture? Let's say those 2 objects, they represent entangled state, like 2 officers, and the size determines amplitude. But you could say, well, but all those states should be different. And now look, this object is the same as this one. So they are not different. Why? So look, yes? Because the phases are missing. And the solution is complete with phases. And here it happens that all those phases are multiples of root of size 20 of identity. So now those numbers here give phases. Here is 0, here is 10, and here is 10 and 10. 10 is minus 1 because of this. So you see this is exactly the orthogonal pair of Bell states. And indeed they are orthogonal. So what you see here, this is the full solution. It's an analytical solution because we know the amplitudes, there are 3 different sizes, 3 different amplitudes. But what you see at the first glance, that somehow the color, let's say the average color is somehow white, and the average figure is also white. But this is not enough, but you can check that all those conditions which were posed are satisfied. So here's the solution in this, say, okay, in the physics way. So okay, this is the state, it's a superposition of 3 and sometimes of 2 states. And those numbers, A, B, C, are very simple. They are known. Okay, so, by the way, the B over A is just famous number 1 plus square root of 5 over 2 is a golden mean. Therefore, we were tempted to call this state golden state. And this is like Pythagoras' theorem here, A, B, and C. So in a sense, it's like has roots in Greek geometry. So this is the final solution. And it's easy to, as usual, it's difficult to find such an object, but easy to check that it works. So I think, okay, this is another version of it. I have to skip the technical details, how we found the solution. I will just mention one thing. So there is just a random search, but at some point we got a huge matrix of size 36. But then we were allowed to use a local transformations. Local means this matrix of size 36. I rotated by U6 times U6 from left and right. In this way, we could make a lot of entries equal to 0. Then, after another turn, we observed that you could make the number of non-zero elements, reduce them to, I think, 144. And then, after permutation, we could see, after this permutation of this matrix, it has such a structure. Now, look, it is a unitary matrix. So now, if it's unitary, it has to be unitary in each block. And now in each block, you can write unitarity condition, and you can solve them analytically. And in this way, we found this state analytically, and we could check that all those conditions are satisfied. So I think, okay, this is relation to geometry to the golden mean, but I think I have to skip it. And okay, this is another version of those quantum officers of Euler in the bridge notation. By the way, you can see a strange thing, like generals, like aces are entangled with queens, with generals, let's say lieutenants with colonels. So in a sense, the entire group of 36 officers can be split into 9 groups, it's important combinatorically, of 9 groups of 4 officers which are entangled together. So we obtained a very simple result, which you will know, that 6 times 6 is equal to 4 times 9, which for us has an important meaning. And I'm almost done. From physical perspective, existence of such a state implies that if you could prepare physical state, let's say exactly this is a 4-dice system. I have 4 objects, 6 levels, so it's exactly 4 dice, and if you could prepare, maybe we will, such a state in this state, then choosing any 2 dices and measuring them, you could predict the outcome on 2 other dices, which is not possible for coins. And now I will, so this is an analytical solution of the quantum version of the problem of 36 officers of Euler, and I think I will just finish with concluding remarks. So main theorem is that such absolutely maximally entangled states of 4 subsystems with 6 levels do exist, and this implies solution of the quantum analog of the famous problem of Euler of 36 officers, and there are some other physical interpretation maybe I will not dwell on right now, but rather I will finish with another remark. So look, exactly 1.5 years we put the second preprint of us, and we wrote in our paper, which is now published, the following statement. It is sad to note that these Russian officers recently left the parade ground in St. Petersburg, where they belong, and went 1,000 miles south. However, explicit analytical results described in this work strongly suggest that the officers might eventually suffer a transition into a highly entangled state. Thank you very much.
Thank you.
So, yes, Maxi.
Is for any classical system for n equals 6 exist, like analog for this question, n equals 4, like for n equals 6 to have the story with.
Okay, so well, so the original problem of 36 officers of Euler.
No, for n equals 6 and some d.
So sorry. Yes. So for I understand now. As in this green-red table, of course, there is such a state for, let's say, quantum, for 6 qubits, and it corresponds not to the Latin square, but Latin cube. And very well. And if you have 8 parties, it's hypercube. And of course, so this is related now to existence of quantum hypercubes, which is more complicated. And then again, it is known that, for instance, for 8 qubits, such state does not exist. Only exists for 6 qubits, in the qubit case.
Yeah, but classical examples.
Yes, their relation. Okay, I forgot to mention they are strong, very related to classical error correction codes. So not any, but many classical error correction codes are related to such configurations. In short, our state provides us a new code of quantum error correction, which allows us to encode 1 dice, 1 quhex, into 3 quhexes in such a way if 1 dice is spoiled, we can still recover information. So therefore, this is one of the meaning I mentioned. Thank you.
Other question? Yes.
Is this solution that you showed us unique in any sense?
Very nice question. So 2 years ago, we were very pleased that we found it. We're of course convinced it's very unique. It will not exist anymore. But a year later, one of our co-authors of this paper, Suhail, found another solution, and now we found another 2. So now there are 5. Maybe there are infinitely many. But it looked like it's impossible to find, but now it occurs, we know how to look for them. So now we know there are many, several, we don't know how many. Maybe infinitely many.
And just to finish my question, this 20 that appeared as a 20th root of unity in the face, is it in all your solution?
It is in our solution obtained analytically, but we do not have a very good answer why 20 and not, for instance, 40 or 36. We are very much amazed with this result, yes. And we don't have any good... Okay, so here are just some, hand-waving arguments concerning, with this Greek pattern, but... okay, so the fact that it is 20, it explains, of course, the appearance of the golden ratio, yes, because, there's a pentagon and the ratio of the side and the diagonal.
Yes,
you showed us these green and a few red points, and if I remember well, n equal 4, d equal 10 was green.
Yes, this is the table of our colleagues, yes, here.
But d equal 10 is not a power of a prime, so it's having troubles with the classical state.
Okay, sorry, but of course, classically, we know, sorry, I forgot to mention this, it was a famous Euler breaking paper in, I think, 57, 58, and there was a great discovery that they do exist, classical orthogonal Latin squares of size 10. Okay. You know this result? Yeah, and then they were found for 14, and then they were proven to exist for any n higher than 6. Yeah, classical. So therefore, our case, in some sense, closes the gap, because this was the only case for which the answer was unknown.
Okay, so there is
moreover, this result was one of the first results of a highly important mathematical result, obtained first by numerical research. Of course, then it was found confirmed analytically. I mean, construction of two orthogonal Latin squares of size 10. By the way, concerning French literature, there is a famous book of La vie mode d'emploi of Perez. Yes, so by the way, this was a book written in like 70s, and there was the house in Paris 10 times 10, and he used this existence of this orthogonal Latin square of size 10. You know the book? No. Who knows? So you see the relation?
Some know. No. I know.
Okay, good. Merci beaucoup. Thank you very much.
Thank
you.